Hi guys, welcome back. Today we're going to continue our discussion of the k-epsilon model. So in the last video we talked about the Boussinesq relation, and we talked about isotropic assumption, and we talked about the Boussinesq equations. Of course, isotropic actually means that the turbulence, like the UU in the x direction, VV in the y direction, WW in the z direction, these are all the same. And usually that will result in uh, isotropic. That's what isotropic thing is about. Um, yeah, and of course we can further assume that mu t, which is the turbulent viscosity, and k, which is a turbulent, this constant here, which is something like the turbulent kinetic energy. These are independent of direction. So yeah, that is something we can assume also. Anyway, because this thing is a scalar, this thing is like, it's supposed to be like a fluid property, so to speak. Yeah, but it may differ from place to place, but usually, yeah, it is the same. Yeah, forget it, it's the same. Yeah, we can make that assumption. That's usually what is the standard assumption anyway. But just to clarify, the true meaning, I mean, if the turbulent flow is isotropic, then this is equals to this is equals to this. That's very fundamental. So okay, back to our k epsilon model. What is k and epsilon, and why do we need to develop such a model? Now I want to bring our attention to first, when we try and simplify, get rid of some unknowns. For example, this average of the fluctuations, we find that we have two new unknowns. One is this, which is the kinematic turbulent viscosity, or if you multiply by the density, it becomes the dynamic turbulent viscosity, and of course this k, which is some turbulent kinetic energy. If you check the units, there is a rho here. There's a rho here, which is density, and there is a delta ij here, which is the Kronecker delta. Then these are dimensionless, and this 2/3 is dimensionless. Therefore, this k is in the units of u squared. So if you know kinetic energy is half mv squared, or if it's per mass, it becomes half rho, or per volume, right? Rather, rho u squared. Or if it's really per unit mass, then it's just half u squared. So this is like a specific kinetic energy that we have. So this is what k stands for. Okay, so it has the units of u squared, and this has the units of viscosity. But now the problem is, how are we supposed to determine this k and this mu? Well, the first place we look at is the k epsilon model. So the k epsilon model basically states that, hey, k takes this form, alright? K is some turbulent kinetic energy. So it will be half u prime square plus v prime square plus w prime square. So it's basically the summation of all the disturbances in the x, y, and z direction. This is the turbulent kinetic energy. And what is mu? Well, for that we actually have to develop some kind of new correlation. So this is what mu will be. Mu, the turbulent kinetic energy, turbulent viscosity, is equals to rho times some constant, some experimental constant, and k squared, which is what our turbulent kinetic energy is, and epsilon. Oops, spell epsilon right. There you go. Right, so we have two new parameters called k and epsilon. And what are k and epsilon? Well, according to this book called the Computational Fluid Dynamics: A Practical Approach, we see epsilon as having this kind of units. So let me just write that down. We already discussed what k is. So this is mu, is the kinematic turbulent viscosity. So I'm going to double bracket u I partial xj, and that goes into, again, the same thing, partial u I partial xj. And beware just that this u is with a prime, right? So this is all the terms pertaining to the instantaneous fluctuation kind of a term. Okay, I'm going to bracket it and I'm going to bar it. Okay, so now let's check out what the units of this are. What is the units of kinematic viscosity? Kinematic viscosity. So nu of t equals to, the units are in meter squared per second, right? And what is the units of this? Well, the speed is in meters per second. This is in meters. So the units of this are in 1 per second. 1 per second. Okay, 1 per second. Let me do that again. So I should copy this over and paste it here. Per second. So let's take a look. Let's rearrange it. Why like caps locking or something? Meter square per second square, 1 per second. 1 per second. Alright, what is this? This is a u squared kind of a unit. And this should be var epsilon. So this is in a kinetic energy kind of a form, specific kinetic energy, so u squared. And this is the rate, is some sort of rate. So this is in a kind of a specific power. So var epsilon, epsilon is in units of some sort of specific power. That means power per unit mass, right? So what does it actually stand for in this model? Epsilon actually stands for rate of Ke dissipation. So let's check. I'm gonna scroll for you in the book and show you. Yep. They say that the turbulent kinetic energy is K and the rate of dissipation of turbulent energy is epsilon. And so are these constants? Unfortunately for us, no. This K and epsilon, they will vary throughout the whole field, just like pressure and kind of velocity. You can't really expect the turbulent kinetic energy to be same throughout the fluid, right? Closer to the wall, the value, it should be lower because there's a no slip condition. If there's a no slip condition, then these velocity fluctuations are just nil. So nearer to the wall, we expect to have lower kind of turbulent kinetic energy. And likewise, if we know that the velocity gradients are, at least these instantaneous velocity gradients are going to change throughout the fluid, we cannot expect the fluid to have the same epsilon throughout the whole fluid, right? So it will have its own conservation equations. So I'm going to quickly go to refer to the textbook, and these are some of the conservation equations here. Now I'm going to type them down very quickly. I'm going to speed it up in the video. And yep, so I quickly poof these two kind of equations out. So one is talking about the kinetic energy, just turbulent kinetic energy. There's a transport of it, and of course with all transport equations there will be, you know, accumulation of kinetic energy within the control volume. These are the advection terms. Is there fluid bringing kinetic energy in and out? And then these are like the diffusion. Looks like a diffusion kind of a term. Alright, so these are like similar to diffusion. Cause they have yeah, diffusion in and out. Yep, so this is the diffusion terms. And this P just stands for production, D stands for destruction. So that means, let's say this is a production rate, this is a consumption rate. It's the same with any, you know, if you talk about heat energy, you have rate of heat accumulation, heat advection, heat diffusion, and then heat production within a control volume, and then heat consumption if there's some sort of endothermic reaction. So it is very similar to heat, the transport of energy in general, right? So and here it's like the same. It's a rate of kinetic energy dissipation. It's a power kind of a thing. How fast does it dissipate? Yeah, so again, the formula is pretty similar for the accumulation advection terms, because these are quite standard throughout, whether you talk about energy or momentum, etc., etc. Doesn't really matter. So as long as the stuff that's in there, I mean the form of the final equations will be more or less the same, because this one will represent the usual stuff, advection, and this is what do you call that, diffusion, and this is the accumulation term, and this of course is some production and destruction, and is adjusted by some constants. There's epsilon, k, and this c is here. So it looks a lot complicated, but honestly this is all for the computer to solve. All we need to know is that what does physical significance of k and epsilon actually mean. And then you'll start to see extra terms popping out like sigma k. This is an adjustable constant across all of them. Again, we assume it's the same sigma k for x, y, and z. So I mean, if we assume it's constant, we can actually take everything out. Otherwise we leave it in there, and usually the assumption is that it's constant, especially for k-epsilon model, and one value is given to fit kind of the experimental data. Same thing for sigma epsilon. It's kind of the same, and these are, you know, these are values that are computed at every time step and every space, so there'll be a distribution over time and space. And these two constants, c epsilon 1 and c epsilon 2, these are also you know, empirical, means you've got to test them out and fit it to your data. So what is P and what is D? Okay, so P, if you look at the textbook again, P here refers to this term. Okay, oops, yeah, P refers to this term, right? So I'm gonna type it out slowly. So yeah, oh sorry, for constant like fluid property I will use this relation instead. So here, so I'll copy this down. Or you know, tell you what, we can discuss P and D in our next video. Well, and if you're not sure where to look for it, you can look for it here. It's a k-epsilon's turbulence model. You can look for expressions of P and D here, but we can discuss it more in the next video. Thanks for watching. If you like it, please leave the like, and a comment in the video comments section, and leave a like here, subscribe as well. Thanks for watching. Thanks for your patience. I'll see you guys next time.